Hello everyone, I hope you're all well. My name is Arash Hashemi. I'm a master's student in Motion Research Group, University of Waterloo. Today, I'm presenting our research with Professor John McPhee about designing a trajectory planner for a human-robot interaction rehabilitation system. This work focuses on a stroke end effector-based robot designed for upper extremity rehabilitation. Research has shown that stroke is the leading cause of adult disability and one of the prevalent causes of global death. This disease has brought about physiological, psychological, social, and economical negative impacts. There are 426,000 stroke survivors in Canada and 50,000 new cases per year. A great portion of post-stroke patients live with long-term disabilities which hamper the normal routine of their life and even interfere with their casual daily activities. Fortunately, the use of robotics has been shown effective in improving the patient's motor recovery. Robots aid patients perform their rehabilitation practices and thus save a great deal of time and energy. Now, during recent years, most focus in the rehabilitation robotics field has been on design and control synthesis. On the other hand, less work has been dedicated to finding the manipulation trajectory, which directly determines the rehabilitation practice quality. A bad trajectory not only does not help with patient recovery, but it also may aggravate his or her condition. Therefore, the goal of this research is to design a framework to systematically calculate the manipulation trajectory. Previous research on this topic divides into 4 general sub-branches. The first sub-branch takes advantage of trajectory interpolation, in which the target points in the trajectory are set manually and functions are used to interpolate between them. The second sub-branch focuses only on robotic trajectory planning without considering the subject model in the framework. The problem with this method is that the final trajectory is less clinically plausible. The third sub-branch uses kinematic level human models in the framework, and finally, the fourth sub-branch uses skeletal human dynamics without considering muscle models. Adding muscle models to the framework has 2 main advantages. First, we have access to muscle level information. So, for instance, we can only focus on a specific group of muscles. Second, we are considering the source of the problem, and hence, our result will be the most clinically plausible. Third, with the progress in muscle modeling research, different models of muscle atrophies can be used in our framework, and the corresponding appropriate trajectory can be designed for each of them. So, the main contribution of our research is using an integrated robotic and musculoskeletal upper extremity model in an optimization-based trajectory planning framework. In this slide, we will discuss the human-robot interaction model that we are using in our framework. This model, which is developed by Qannari et al. In 2015, consists of a robot model and a human arm model. Our robot is a fully actuated 2 degrees of freedom planar mechanism. The arm is modeled as a 2-dimensional linkage with 6 muscles which are lumped from the 29 muscles in the full 3D arm model. Heel type models are used for muscle dynamics. The arm interacts with the robot by grabbing the end effector, which is equipped with a force sensor, and the robot can perform rehabilitation practices in the horizontal plane. The 2 systems are integrated by a passive revolute joint on the end effector. Using a kinematic constraint, the final human-robot interaction model is shown below. The terms with subscript A refer to the arm, and the terms with subscript R refers to the robot. We consider the robot angles and angular velocities as the states, and robot torques and muscle activations as the inputs. For the planner, we are taking advantage of Direct-Collocation Optimization. Note that in contrast to shooting methods, this approach considers both the states and the inputs as the decision variables, thus enabling us to produce the trajectory. In this method, the continuous optimization problem and constraints are first discretized and then solved. On the right, we have defined boundary constraints on the states, which correspond to the limitations in the workspace of the human-robot interaction model. We have also defined boundary constraints on the inputs, which correspond to the hardware specifications of the robot and physiological limitations of muscles. The initial and final time is fixed. We have also defined the initial and final end effector position, which can then be mapped to initial and final robot states using the inverse kinematics. To formulate and solve the problem, we have used the open source OptimTraj library in MATLAB, developed by Kelly in 2017. For the cost function, we are considering the robot input rate, arm muscle activations, and arm joint accelerations. The last two terms are suggested by Barrett et al. In 2011 on their research about finding the best cost function for arm reaching movements. For the discretization, we have used trapezoid transcription methods. Linear splines are considered for approximating the control profile, and quadratic splines are considered for approximating the state profile. Note that the target points in this case come from the optimizer, and in this sense, this method is different from trajectory interpolation. The planner will output the desired manipulation trajectory. It will also provide the open-loop inputs to follow that trajectory, which works well in simulation. However, we need to employ a state feedback controller to stabilize the trajectory for experimental implementation. In this research, we have used LQR controllers. LQR is particularly useful for planar mechanisms. Since the gravity is counterbalanced with the plane, there are infinite stable points and linearization around any point in the workspace will be valid. In order to find the LQR input, a Riccati equation needs to be solved at each iteration. Now, we can use two approaches to implement the controller. First, we can use force sensor data and consider the human-robot interaction model online to calculate the human muscle activations and robot torques at each iteration. Second, we can only consider the robot model online and calculate the patient's contribution by using force sensor data, converting patient's force to robot torque by using Jacobian matrix. The robot can then provide the remaining required torque at each iteration. Note that both approaches will result in a suboptimal trajectory since the torques and muscle activations will not be exactly the same as the open loop values. Having said that, considering that the second approach is faster, we will adopt the latter strategy. Here is the general scheme of our planner and controller. The planner runs offline and produces the state input trajectories. These values are then utilized in online control within the LQR framework. At each iteration, the low-fidelity robot model is linearized around the trajectories, and then the linear model is used by LQR to produce the input. The input is then applied on the robot to produce the next state for the next iteration. This process continues until the end of the desired trajectory. In this slide, you can see the trajectory optimization results. On the top, the end effector position is shown in X and Y coordinates. The initial and final points are chosen such that the internal rotation of the arm is prohibited, because reportedly this practice is ineffective in patients' motor recovery. On the bottom, you can see the open-loop robot inputs and muscle activations. The MapleSim simulation of the trajectory is shown on the right. The inverse dynamic model of the robot is utilized to produce the inputs in the simulation. Using the LQR controller, we have been able to stabilize the trajectory. Good accuracy is obtained both on the position and velocity level in simulation. The inputs are higher than the open loop values since we are not considering the human inputs here. We are using a Quark interface connected to Simulink to apply the controller on our experimental setup in real time. The robot updates at 500 Hz frequency, which is a high update speed. The real-time control results are shown on the left. The black lines indicate the two standard deviation of the values at each instance. The trajectory is successfully tracked using the stabilizer. Due to COVID situation, we have not been able to test this controller on stroke patients and thus consider it for our future research. To conclude, in this research, we have used a human-robot interaction model with muscle dynamics in an optimization-based trajectory planner. We have calculated the desired trajectory for a stroke rehabilitation robot and have used a feedback controller to stabilize the trajectory in simulation and real time. Our future work will include testing this controller on stroke patients, testing the planner with other controllers, and making the planner fast enough to be applied in real time so that we can choose multiple initial and final points and acquire the trajectory instantly. In this slide, you can see our references. Thank you very much for your attention. I will be happy to answer your questions.